And hopefully this is recording. All right, it's 8:20. I have to keep an eye on participants and admit them as they come into the waiting room. Okay. This is the way we're going to function for the rest of the semester. Hopefully there won't be any glitches. And I'll be recording and uploading the links as usual for those who can't join us live. But otherwise, I'm going to operate the way I normally did in class. So let me start with announcements. And you are allowed to participate. You should be able to unmute. Please keep muted unless you want to ask a question, then you can unmute, or you can type in the chat box, whichever you're more comfortable with. By way of announcements, I sent an email a little earlier this morning. I have now graded midterm 3 and uploaded the graded work, your score, and my solution to Blackboard. So you can check all that out. You can check your graded work. You can check my solution. As I said in the email message earlier this morning, given the mean and the median for this exam, the median was a C. I tend to curve or shift, I should say, the median so that it's a C plus. So I added 5 points to everybody's score. It's not a curve, it's a shift. Everybody got 5 points. And so you should see that reflected on your grade. In terms of what's coming up next, homework is due tomorrow night, Tuesday night. Just so you can plan ahead, the next set will be due next Monday night. Okay, after we come back from Thanksgiving break. In terms of lab, I need your lab reports for experiment 7 either today or tomorrow. And I will be uploading to 110L on Blackboard the instructions and the data for experiment 8, the last experiment, which is on transverse waves on a wire, which is the topic we've been studying, transverse waves, in chapter 16. So the timing for the lab is right up with the book and our class. And so remember, the way this last experiment will work is you still work with your partner or partners. I've given you the data. You'll see it when you log into Blackboard. And I'll also have instructions. And then you will, in essence, do the analysis and answer questions. And then turn in a lab report for you and your group, to Blackboard as a single PDF, the way you do any other lab report. And that will be experiment 8. And that will be due the last day of classes, which is Friday, December 4th, the end of the week after Thanksgiving. And then the week after Thanksgiving, we're going to be studying chapter 17, which is a continuation of waves. And we're going to focus on longitudinal waves as opposed to transverse waves. And our focus with longitudinal waves will be on the most common kind of longitudinal wave, which is a sound wave. Okay, those are my announcements. And let me now get set up for what I want to talk about. And that will give anybody a chance to ask a question if they have one. Okay, so today,
hello.
Oh, question?
Yeah, are we having lab today?
No, as I explained, we're not meeting in the lab room. I'm going to be providing the data for this last experiment, experiment 8. I'll be uploading it to Blackboard later today. And you will go there and you will get the data for experiment 8. That's what you would have done in lab today. But I'm providing that data just because with all of the situation with COVID and a lot of people having left campus already for reasons I completely understand, it just doesn't seem very reasonable to have in lab work this week. Does that make sense? So I'm giving you the data. It will be on Blackboard. That's what you would have done in lab this week. You work with your partner on analysis and turn in the lab report the end of next week. Okay? Okay. All right then. Today's topic, you can see the learning objectives. I'm sharing with you my OneNote screen. And this would be just what I would be showing you on the projection screen in the classroom. The learning objectives, we're focusing on section 7 in chapter 16, standing waves, and what's called resonance. Very important and quite common phenomenon in the natural world. There are a lot of learning objectives, so I'm going to highlight the important parts and write down a few of the key equations. But these things were in my lecture video for today, so I'm just going to mention them briefly here. Learning objective 1, for 2 overlapping waves, same amplitude and wavelength, we'll just choose that for simplicity. And here's the key thing, traveling in opposite directions on the same string, we are to sketch snapshots of the resultant wave indicating what are called nodes and antinodes. Well, I showed you animations of what happens when you have 2 waves on the same string at the same time, but traveling in opposite directions. That's the key thing. And you get what's called a standing wave. And the animation that I showed you in the video lecture, I think shows pretty clearly why we call it a standing wave when you see it animated in time. It's very clearly not traveling. You can see it when you watch it. So what this objective really means is they want you to realize that what you get is called a standing wave, and that there are certain x values, certain points along the x-axis that never move up and down, certain points on the string that never move up and down. And those are called nodes of the standing wave. And other points on the string, halfway between nodes, are points on the string that have maximum up and down motion, maximum amplitude. And that maximum amplitude is twice the original amplitudes of the 2 waves that interfered. And those points with the maximum amplitude are called antinodes. So they just want you to understand that when you combine 2 waves traveling in opposite directions, you get what's called a standing wave. Learning objective 2. For these 2 overlapping waves with the same amplitude and wavelength traveling in opposite directions, find the displacement equation for the resultant wave and calculate the amplitude in terms of the individual wave amplitude. I want to write a little bit about that. So let me write that down here. So let me write down the 2 wave equations that represent the waves we're going to be adding together. That means we're going to let them interfere with each other. Wave 1 has a wave function of this form. It's a sinusoidal traveling wave with an amplitude y max, angular wave number k, angular frequency omega. And because of that negative sign inside the sign, that represents a traveling wave traveling in the plus x direction. Now let's write down the wave equation for wave 2. Same amplitude, y max. Sinusoidal wave. Same k, so kx, but now plus omega t. And I'm going to do something I didn't do in the video lecture. I'm going to do something a little bit different. I'm also going to let wave 2 have a phase shift relative to wave 1. So the one key thing is that wave 2 is traveling in the negative x direction. That's what that plus sign means. And I'm allowing wave 2 to be shifted relative to wave 1. I didn't do that in the video lecture, just for simplicity. The net wave is what you get when you algebraically add the 2 functions, y1 and y2. And I did that in the video lecture, albeit with a phi equal to 0. I'm going to write down what you get. You have to use a trig identity because you're adding 2 sine functions. The result is 2y max, because we're putting 2 waves together, each with an amplitude y max, sine of kx plus phi over 2 times cosine of omega t plus phi over 2. If you want to compare that with what I did in today's video lecture, just set the phi to 0. And we call this the wave part, or at least think of it this way, this part, because that's the oscillating part. It depends on time. So the amplitude of this net wave is the absolute value of everything else except the oscillating part. So the amplitude is absolute value of 2y max sine of kx plus phi over 2. Okay, and that's what they mean by finding the amplitude of the net wave. They mean use that formula. Note the amplitude depends on the x value. Where are you on the string? Where are you on the x-axis? And that will determine what the amplitude is. Again, what I talked about in the video lecture is just like this, except the phi was equal to 0. All right, 16.7.3, describe the simple harmonic motion of a string element at an antinode of a standing wave. That goes with learning objective 4. For a string element at an antinode of a standing wave, write equations for the displacement, transverse velocity, and transverse acceleration as functions of time. Let me do that, because that may be a little bit of a stretch for you to see what they're talking about. So I'll do 16.7.4, I'll write it right in here. Okay, they decided to focus on an antinode, and with good reason, because those are points on the string, on the x-axis, that are moving up and down with the biggest possible amplitude, and that being 2y max. That occurs when the amplitude formula I just wrote down, when the sine function equals 1. That's what happens at an antinode. That sine function equals 1, and you get a maximum amplitude of 2y max. So the y equations, the y displacement at any of the antinodes, any of them, I'll write it like this: y subscript an for antinode. And it's only going to only be a function of time, because the x value is now set at whatever the antinode locations are. So the amplitude is 2y max, and the oscillating part is the cosine of omega t plus phi over 2. That's just this formula for y net right up here, that whole formula, but put the sine function equal to 1. That means you're at an antinode. And that's the formula for finding the y displacement of any of the antinodes. To get the transverse velocity, we've been using the symbol u for the up and down velocity of a string element in this chapter. So to get the transverse velocity of any of the antinodes, it's a function of time, just take the time derivative of the y function of the antinodes. The velocity is y derivative, and use the chain rule on that 2y max cosine of omega t plus phi over 2, and you get negative omega 2y max sine of omega t plus phi over 2. And that's what you would use to find the transverse velocity, the up or down velocity of a point, a piece of string that's at an antinode, a point of largest amplitude. I'll let you figure out the formula for what they call the transverse acceleration as a function of time. Hint is it's going to involve one more derivative of the transverse velocity. 16.7.5, I'm not going to say a lot about. It talks about what are called hard and soft reflections of string waves at a boundary. So what they want you to think about there is you got a taut horizontal string. You're holding one end. The other end could be tied to something, let's say. And then you move the end you've got up and down with simple harmonic motion to make a sinusoidal wave. It's going to travel down the string. What's going to happen when it gets to the end where the tie is? Because that end of the string is tied, it can't have any up or down displacement. You get a reflected wave going back from that hard reflection, and the waveform gets inverted. I'm just telling you that fact. You want a little bit more information about that? Read section 7 in the book. Or you could have what's called a soft boundary condition at the end, where the end of the string is free to move up and down. Maybe it's on a kind of tied to a ring that can slide up and down a pole freely. Then what you get is a reflected wave, and the waveform is not inverted. It's going same direction as the incoming wave. The reason that's important is for the last two learning objectives. What is called standing waves on a string. And it involves the concept of resonance. and it involves a string. One end is fixed, the other end is moved up and down with simple harmonic motion. It doesn't have to be moved up and down very much. And so you get a traveling wave going down. At that hard end, you get a reflection back, and you've got this complicated combination of waves going in both directions. Well, that's exactly what I've just been talking about to create a standing wave. Waves on the same string at the same time, but going in opposite directions. But normally, when you add together those waves going back and forth in opposite directions, you get a pretty complicated, jumbled mess. But if the frequency of the driving of the sinusoidal wave is just right, you'll get reinforcement of the incoming and the reflected waves, and you'll get a situation called resonance, and you'll get a really big amplitude of a standing wave on the string, and you'll be able to see it. And that's the one bad thing about not being able to be in the lab this week, for you to actually take the data for this experiment, transverse waves on a wire, because you will make that very situation happen if you were in lab, and you could see the wire vibrating in resonance in the standing waves. And people who are musicians and play stringed instruments really love that. And that's the sad thing, we're not going to get to see it. But the point is that, let me get myself some room here. When you get these so-called resonance conditions and get very big standing waves on a wire, there are very simple relationships that have to be true. And in 16.7.7, it says, in terms of string length, determine the wavelengths required for the first several harmonics on a string under tension. And I will just tell you what those are. You can only have certain wavelengths, lambda, and we're going to put a subscript n, and you'll see why. And those must be equal to 2 times L. What's L? The length of the string. 2 times its length over n. What is this n? It just stands in for any positive integer. N starts at 1 and goes up by integer steps. And we put a little subscript n on the wavelength formula to remind us that there's an integer here, n, in this formula, and the wavelength is 2L over n. And I drew pictures on the video lecture for today showing you what these standing wave resonances look like for several of the first few n values. And these resonances are called harmonics. And again, if you're a musician, you've probably heard that word. Okay, those are the n equals 1 is called the first harmonic standing wave. N equals 2 is called the second harmonic, and so forth. And the wavelengths get progressively shorter as the n gets bigger. Then the last learning objective, 16.7.8, says, for any given harmonic in one of these standing waves, apply the relationship between frequency, wave speed, and string length. Well, what they mean is this. There are only certain frequencies for these harmonics, f sub n. And they are given by n times the frequency of the first harmonic, f1. And that's n times the speed of the wave v over the wavelength of the first harmonic, lambda 1. But the wavelength of the first harmonic, lambda 1, is 2L from the formula for lambda. And so this is the formula that it's referring to right here. Whoops. N V over 2L, right here. That's the formula it's referring to. Well, remember, the n is any integer in that list. 1, 2, 3, 4, dot, dot, dot. And those are the frequencies you have to see a nice big standing wave resonance on the string. Also, let me remind you that the speed, that's the speed v of the traveling waves that are going in opposite directions that interfere to make this standing wave. And we had a formula already in this chapter for the speed v of a standing wave on a stretched string. It's the square root of the tension in the string divided by the mass per unit length, or linear mass density. So that's the key relationship that you're going to be testing in this last experiment in lab. That relationship for the frequency as a function of N, V, and L, where V is a function of tension and mass per unit length. That's the key relationship for the harmonic frequencies of a standing wave on a wire. So what I'd like to do is do a little bit of applying of that. Let's start with this picture right here, which shows schematically some standing wave resonance patterns for a couple of strings. So let me read to you what the practice question is about, and then we're going to solve it together. Okay, here's the situation. We have two strings, as you can see. Well, they're called A and B. They have exactly the same length and the same linear density. That's the same mu, mass per unit length. But string B is under greater tension than string A. Okay, now the figure shows four different situations labeled little a through little d, in which standing wave patterns have been created on each of the two strings. And they go together. So for picture little a, string A's standing wave pattern's on the left, while string B's standing wave pattern is on the right. And for little b, you can see the pattern of A and the pattern of B. And for little c and for little d. And your book wants you to be able to see these little drawings like this and actually be able to tell just from these drawings which of the standing wave resonance modes has been excited. Which value of that integer little n, which harmonic? Is it n equals 1, the first harmonic, n equals 2, the second harmonic, etc. They want you to be able to look at that picture and just tell. We'll talk about that. Here's the actual question for this practice. In which of the four situations, little a through little d, is there at least a possibility that the strings, big A and big B, are oscillating at the same resonant frequency? They're oscillating at the same frequency. All right, that's what I want us to figure out. So let me say a few words to get us going. All right, now the key formula for the frequency of oscillation is that one right up above that I highlighted in yellow, right there. That's the formula for what are called the FNs, the harmonic frequencies. Notice it depends on V, and V depends on the tension. But the formula also depends on L and mu and N, which particular harmonic has been excited. What's the integer N? So your first inclination might be to say, okay, let's look at these situations one at a time, A through D. Let's practice first with just looking at these schematic drawings and identifying what harmonic the string is oscillating in. What's the N value? What's the integer N? 1, 2, 3, 4, what is it? So let's look at string A in situation A. So they're showing me that at a certain moment in time, the string is up like that. That's its shape, like a snapshot. And exactly half a period later, it's down there. And the dash line is just meant to show you that it's a half a period later. And then half a period after that, it's back in the top one. And half a period later, it's back on the bottom one. And it just goes up and down and up and down. That's the longest wavelength standing wave you can have. That's the first harmonic, n equals 1. Notice it has one antinode, highest amplitude, right in the middle. If that's n equals 1, what is string B doing in this case? What oscillation number is it? Anybody want to take a guess? You can type in the chat, or you can just say, unmute and say.
2.
2. This one right here is in n equals 2. The second harmonic, notice it has two antinodes, two points that have the largest amplitude. Okay, so you need to be able to identify what the mode is just from the picture. Okay, now, with that in mind, notice that in none of the situations are the two strings oscillating in the same mode. Yes, in neither little a, nor b, nor c, nor d do those two strings oscillate with the same value of n. So one's first inclination might be to say that none of those frequencies are the same because the frequency depends on n. And in none of those cases do the two strings have the same n. However, it's not that simple, is it? Because remember the statement that it says string B is under greater tension than string A. Notice what the tension does. It influences the V, the speed of the traveling waves that interfere to produce this standing wave. And the V is right there in the frequency formula. Bigger V, bigger frequency. So you see where this is going maybe? For string B, for a given n, it will have a higher frequency than string A at that same n, because string B is under more tension. With that in mind, can you look at the picture, take a minute and think about it? Can you find one of the four situations where it's going to be possible that the two strings have the same frequency? Little a, little b, little c, little d. Anybody want to say? You can either chat or unmute.
C.
So we've got to vote for C. It looks like string A is in the first harmonic mode, n equals 1. And string B is in, that would be the third harmonic, n equals 3. Okay, we've got a suggestion, so let's go ahead and work it through. Okay. So we've got a kind of an intuitive answer, but if this were a question on a quiz or an exam, I would want to see some kind of reasoning, of course, as you know full well. So let me show you, let's talk through how you would work out the answer to this. Let's note that both strings have the same mu, same mass per unit length, and the same length. Let's note that. Let's also note that the tension in B, that's how I denote tension, Ft. Oh, Vinny wants to say hi. The tension in B, oh, I can write better than that, is larger than the tension in A. We know all those things. Let's now write down a formula for the harmonic frequencies that are possible in string A. I'll label it Fa. Now I'm going to label it with some care. All right. There's that integer n, but I'm going to label it n sub A. So n sub A over 2L, square root of the tension in A over mu. And n sub A is the harmonic index that tells us which harmonic the wave is in, but specifically for string A. Now let's write down the same expression for B. And now I'm going to label it n sub B over 2L, square root of tension in B over mu. Notice the labeling like that, something like that, with an n sub A and an n sub B is really important because I've got a separate F formula for each string. And I can't just use n for each because the n's don't have to be the same. Look at our pictures. In none of those four cases are the strings in the same n. So you need some kind of labeling scheme, like I did here, NA and NB, to denote that the n's in the frequency formulas for the two strings do not have to be the same. Now, what I find to be useful in this problem is to take these two expressions and take the ratio of them. Let's write the formula of what we get when we take FA over FB. and take those two expressions and put the expression for FA over FB. Here's a key thing. The factors of L and mu cancel because they're the same in the two formulas. The L and the mu are the same. And what I'm left with is, well, I'll write it like this. NA over NB times the square root of tension in A over tension in B. That's what I get when I form the ratio of those two frequency formulas. Now, here's the next key thing. I'm interested in the case where the frequency of oscillation on the two strings is the same, if possible. And of course, that would mean the value of that ratio, FA over FB, was 1. So let's see, let's put that in there, equals 1, and see what we learn about the NA and the NB. Okay, well, so now I'm focusing specifically on that equality right there. And if that's true, I can write it like this. NA over NB equals square root of tension in B over the square root of tension in A. Notice I just did algebra and cross multiplied. So now I have the tension in B upstairs and the tension in A downstairs. But remember, I'm told that the tension in string B is greater than the tension in string A. So I know that ratio inside the square root is bigger than 1. And the square root of a number bigger than 1 is still bigger than 1. So what has to happen is that ratio of the ends has to be bigger than 1. Or to say it another way, by cross multiplying, NA must be larger than NB. That's the way you get the two frequencies to be equal, at least to have a chance of them being equal, is the oscillation mode in string A has to be higher than the oscillation mode in string B. And that's how you make up for the fact that string A is under less tension. So now you got to look at all these cases and you got to see in any of the 4 cases, is string A oscillating in a higher harmonic mode, a larger N value. So this right here is NA, this is NB. So in case A, NA is 1 and NB is 2. That doesn't satisfy this inequality. It can't be case A. In case B, NA is 2. You need to be able to see that just by looking at that picture. And NB is 3. That doesn't satisfy my inequality. It's not that case. Case C, NA is 2, NB is 3. Well, that is not with an NA larger than NB, so that doesn't satisfy my inequality. Lastly, in case D, NA is 2, NB is 1. Ah, there we go. I have the mode of oscillation. Well, string A is in the second harmonic. String B is in the first harmonic. That at least satisfies this inequality. There's a chance that those two frequencies are equal. All we wanted to know was there a chance? Is it even physically possible? Whereas in the first 3 cases, it's not even possible. Okay, now that's kind of typical, more conceptual practice than anything. There's not too much math, but I did want to show you how you can make the argument quite concretely about which situation it would be. Okay. So the other thing I want to do in today's class is a Wiley plus problem, standard homework type problem for a standing wave on a string. So let me show you that one. I took it out of your book, chapter 16, number 56. And it doesn't have a lot of words, but it asks a lot of questions. So let's go. Let's see what we can do. Here's what it says. We've got a standing wave pattern on a string. It's described by, there's the formula. Now let me pause and say something first that's important to note. We need to be, this is one of our learning objectives, or more than one. we need to be able to identify when given the wave function, the function y of x and t, we need to be able to identify whether we have a traveling wave or a standing wave right from the function itself. Let me emphasize again how you know. If you have a traveling wave, the wave function will have this generic form, y max sine of kx minus omega t plus phi. And it doesn't have to be a sine function. It can be a cosine. In fact, if all I said is a traveling wave, it could be any function whatsoever, but the argument of that function has to have that combination right there. A constant times x plus or minus, I should write plus or minus, a constant times t. That combination together, a constant times x plus or minus a constant times t. Then you know you have a traveling wave. Look at the formula I just highlighted in this problem. Notice it does not have that structure. It does not have a constant times x plus or minus a constant times t. What it has, the structure, is a constant times x inside one trig function, a sine, and a constant times t inside another trig function. That is not the pattern of a traveling wave. It is, in fact, the pattern of a standing wave. We call this part, the time-dependent part, the oscillating part. And then the absolute value of everything else, we call the amplitude. And so we have a standing wave of that form. They tell us that x and y are in meters, whoops, and t is in seconds. So that just gives us units for everything. Remember, the arguments of the trig functions themselves will be radians. So here come the questions then that go, they just want to see if we understand what information that function is telling us. A, for x greater than 0, greater than or equal to 0, what is the location of the node with the smallest value of x? And then the node with the second smallest value of x, and the node with the third smallest value of x. So what they're trying to get us to note here is that a node means that the net y, the net displacement y, is 0 for any value of t, any t. Those are points on the x-axis on the string that never move up and down. We need to find where those x's are. Well, look at the amplitude function. The amplitude involves the point 0040 and the sine of 5 pi x. And the way I'm going to get a 0 for that amplitude, a 0 value, is if the sine part equals 0. So what we need is sine of 5 pi x. I'm going to actually write it like this. Sine of kx to equal 0. The constant multiplying the x in a wave function is k, the angular wave number. That's what we need to equal 0. Okay? So I need the x values for which that happens. That means, and I'm going to call those x values x sub n. N stands for node, because those are going to be locations of the nodes. Now here you got to remember your trig. You got to know everything there is to know about the sine function or the cosine or the tangent. Namely, for what values of its argument does a sine function equal 0? Answer, any integer multiple of pi, including 0. So I'm going to write that like this. K sub n equals n times pi, where n stands for any value in this list, 0, plus or minus 1, plus or minus 2, plus or minus 3, dot, dot, dot. Okay, that's a way to represent where the sine function equals 0. Okay, and that's going to tell me the x locations of the nodes on this standing wave. So all I have to do is solve that little equation for xn. That'll be n pi over k. And now plug in the k value. The k, as I said, is the constant multiplying the x in the sine function. And so the value of k is 5 pi. And let me add the units. Radian per meter. And there's really a factor of radian with that n pi. And now let's simplify. Pi's cancel, radians cancel. I end up with n over 5 meters, where the n values come from that list right there. And the smallest x node, so I'll call that x0, is what you get when you plug in n equals 0, 0. So the origin is going to be a node. The next one, I'll call it x1, is what you get when you plug in n equals 1. So that's 1/5 of a meter, or 0.2 meters. The next one will be what you get when you plug in n equals 2. That's 2/5 of a meter, or 0.40 meters. And it goes on, dot, 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 for however far you can go. And that's where the nodes are. Those are the x values on the string that will never move. And we've answered part A. It's just trying to ascertain if we understand the standing wave wave function. Let's look at B. What is the period of the oscillatory motion for any non-node point, right? The nodes never move, so it can't apply to those, but any other point that's not a node is moving up and down. What's the period of that up and down simple harmonic motion? And it is simple harmonic. Capital T. Just remember this handy formula from earlier in the chapter and from chapter 15. The period equals 2 pi over the angular frequency. And the angular frequency is the constant multiplying the t in the wave function. So I just have to look up at the wave function I'm given and find the constant multiplying the t. That's 40 pi. Now let's put units. 2 pi is a radian, and the 40 pi is a radian per second. Pi's cancel, radians cancel. This is going to have units of seconds. It's going to be 1 over 20 seconds, which is 0.05 seconds. That's the period. Every point that's not a node goes up and down, and we have simple harmonic motion. Okay, somebody's asking a question about part A. Go ahead.
Can we substitute negative values for n?
You can, but it said for x greater than or equal to 0.
What would it physically mean?
It would just
Having a
mean
negative
that,
value for
remember,
x?
we're assuming in this particular problem, if they just give us a wave function for a standing wave, you are to assume it's a very long string. And so this would just mean that these are values on the string that are to the left of the origin.
Okay.
Okay. All right, so we've done B. Now let's do C. What is the speed of the 2 traveling waves that interfered to produce this standing wave, right? I had 2 traveling waves going in opposite directions. That's how you get a standing wave. How fast were they going? What was their V? Well, what you need to remember is that if you get an output standing wave, that's the form we have right up above, then here's the form of the waves that were combined. There'll be 2 of them, of course. One of them was traveling in the plus x direction, and the other was traveling in the negative x direction. And they don't have any phase shift, and I know that because my standing wave functions up there don't have any plus constants after the 5 pi x and the 40 pi t. If there were phase angles, they'd be plus phi over 2 after each of those. Now, each of those is traveling waves, and there's a handy little formula when we talked about traveling waves. The speed v of a traveling wave can be easily computed if you know the constants k and omega. V is omega over k, the angular frequency over the angular wave number. The angular frequency is 40 pi radian per second, and the k is 5 pi radian per meter. Radians cancel, pi's cancel, and you just get 8 meters per second. That's how fast the two waves were traveling. The two that interfered to produce this one, which doesn't travel, it stands still. D, what is the amplitude of the two traveling waves that interfere to produce this wave? Well, again, the thing to note, in addition to the two functions I just wrote down in C for the original waves, y1 and y2, the function for the net wave, that's what we're given at the beginning of the problem, is 2y max sine kx times the oscillatory part, cosine of omega t. You need to know that too. And the point is that in the formula for the net wave, and that's what we were given, the number out front of the two trig functions is 2y max, 2 times the amplitude of the original waves. Now, going back up to the function I was given for the standing wave at the beginning, that constant out front is 0.0040 meters. So that means 2y max is 0.0040 meters. So y max, of course, is that divided by 2. So the original waves that interfered to produce this standing wave each had an amplitude of 0.002 meters or 2 millimeters. Okay, all right, so if you understand the information that's contained in here, there's a lot that one can say. And there's just one more part here. For any time greater than or equal to 0, what is, for t greater than or equal to 0, I should say, what is the first time that all points on the string, that all points in the string have 0 transverse velocity? Then the second time and the third time. Let's make sure we're clear on what they're asking here. Okay, you've got to imagine a standing wave on a string. It's going up and down and up and down and up and down like this. Okay? There are moments in this up and down motion where every single piece of string is at rest. In the up and down motions, talking about transverse velocity, up and down, not sideways. We have to find the times when that happens. Okay. All right. If they want transverse velocity, again, that means up and down velocity. We're not talking about what you would call v, the speed of the traveling waves. The up and down velocity, remember the symbol for that is a u, which is technically a function of x and t. And the way you get it is you take the wave function for the net wave, and you take a time derivative. But because the net wave is a function of x and t, you have to take a special kind of a time derivative, one in which the x is treated as a constant. It's called a partial derivative. You just go to the y-net formula, and you treat x as a constant, along with y max and k and omega. They're all constants. So you have to just apply the chain rule to this function up here at the top, where everything's a constant except t. And of course, you're differentiating cosine of a blob. That's negative sine of blob times the derivative of the blob. Got to be able to do the chain rule and do that time derivative correctly. So what I get for the function for the transverse velocity is negative. When I do the chain rule, I get a factor of 40 pi out front. There was the constant 0.0040. The sine of 5 pi x, that's just a multiplicative constant. Then the cosine of 40 pi t has become sine of 40 pi t from the derivative. Derivative of cosine is negative sine. That's why there's a negative out front. And now what we want is we want values of t, little t, for which u equals 0 for all x. I want every piece of string to be at rest. Not just a few, all of them. Okay, so I have to get this expression to equal 0 no matter what the x value is. And the way we get that to happen is by having that equal 0. Then we'll have to find the particular times when that's true. But if I make that sine of 40 pi t equal to 0, then it doesn't matter what the x is. The u will equal 0. So what I need is I need sine of 40 pi t to equal 0. And again, you need to understand everything there is to know about the sine function. And I just know that that's when the argument 40 pi t must equal 0. I'm going to put a little m on there. And actually, it must equal m times pi, where m can be 0, or plus or minus 1, or plus or minus 2, ... And then I divide everything by 40 pi, and I have the m values. Excuse me, the t values. This would be in radian per second down here, and radian up here, and the pi's cancel, and the radians cancel, and you get m over 40 seconds. And then you just start plugging in the m, starting with 0. So the first time is 0, at least greater than or equal to 0 the first time. Then the next one is when m equals 1, which is 1/40th of a second, or 0.025 seconds. And the next one is when m equals 2, which is 0.05 seconds. And it goes on, ... But we found the first 3. Okay. All right, so that's a standing wave. It's going up and down, right? It's got nodes at particular locations. We found out where those are. And it's got certain times when every piece of string is at rest. And we found out what those are. Okay. All right, I'm out of time, so I'm going to pause for today. Let me know if you have questions as you're working on lab. Otherwise, have a good break for Wednesday, Thursday, and Friday. And then we'll have our next class like this next Monday. Okay? All right, and if anybody wants to stay by and ask me a question, you're welcome to do so.
Thank you.
You are welcome. I'm going to stop the recording though.